For problem 1, we start by designing the model that simulates the system of a double pendulum, using the BioReam Builder tool, trying to make the closest thing to the real system. Now, we develop the dynamic equation of the system using Simulink in MATLAB. As you can see, the equation is a little bit complex. However, our objective is to obtain the output values of the system, which are the angles formed by the mass 1 and the rope 1, with the platform to introduce them into the virtual model and thus observe the movements that the equation represents. For the second problem, we represent the equation in a MATLAB script that allows me to pass the parameters of the equation to the 3D model through objects that reference the translation of the ball. Now, with the model created, we can see the movement of the object.
In the third point, to get the dynamic equation of the system, it was necessary to make an electrical equivalency of the system. If see the basic behavior of the respiratory system, we can realize that it's only a one-way conductor tube connected to an elastic compartment. This model is analogous to an electric circuit that consists in a resistor and a capacitor. One power supply replaces the pressure generated for the muscles, and the electric current represents the airflow. In this model, the pressure, volume, and flow are variables, while the resistance of the way area and the compliance are constant values, which are analog in this case to electric resistance and capacitance respectively. The 3D model of both lungs was created in Blender and later exported to the 3D environment. The difference between the two scenarios lies in the respiratory frequency. When somebody walks, the respiratory frequency is approximately 15 cycles per minute, while when running, this increases to a need of 50 cycles per minute. For make this, the power supply was substituted for a pulse generator and the pedal was modified for each scenario. The difference of the frequency could be observed in the animation of the response of the system. The first animation corresponds to a walking and the second to running.
Okay, for our last point of this project, we needed to make a virtual model of a bouncing ball in a flat surface. This ball has a parabolic trajectory, and the first thing that we do was the model. A very simple model that consisted in a simple flat surface and a sphere which obviously represented the ball. Then we did the dynamic equation that goes as this. In the upper part, we have the first dynamic equation. Because of the parabolic movement, it has two different dynamic equations. The first one controls the movement in the x-axis and the other one represents the movement in the y-axis. In the x-axis, what we have is a simple initial speed that decreases across the time, as we see in here, until its movement is almost zero. And in y, what we have is a ball with an initial speed in g that is accelerated by the gravity, and when it touches the floor, it changes its direction and loses some of its energy until there is none. As we can see in here, it bounces, and every time it bounces, it loses some of its energy until there will be no energy left. And these two equations control a single object in the model, and what we see when we play it is this. As you can see, it bounces until it loses all its energy almost at the end of the surface. So thank you for your attention.